Hello, everyone. So welcome to the session, the Naval Hydrodynamics 2. So in this session, we have three presentation, and the first speaker is the Min Ho. So Mr. Ho, please. Yeah, please switch on your camera and your microphone. Yes.
Hello everyone. My name is Min Ho and I'm Master Candidate in Seoul National University. It's my pleasure to present today. I will start my presentation. Today, I will talk about computational fluid dynamics simulation of energy-saving vortex link cluster using the quanta effect. Presentation content as follows. I will follow this sequence from introduction to summary and conclusion. Introduction part. The propulsion system of the unmanned underwater vehicle, so-called UUV, can be classified as a propeller propulsion system and a jet propulsion system. In recent studies, one of the jet propulsion system, a VRT, was applied for the propulsion system of the UUV due to low noise generation, elaborate control, and maneuverability. VRT has lower propulsion efficiency than a propeller when the UUV moves at a constant speed. So it is required that development of propulsion system with higher propulsion efficiency than the VRT. Meanwhile, the quanta effect is natural tendency of a fluid to attach itself to a curved wall and adhere to nearby surface, which discovered by Romanian scientist Heli Quanta in 1931. The flow along the curved surface induces a lower pressure and attract the surrounding fluid, which is relatively higher pressure. In real life, there are various products that using the quanta effect. In this study, we designed the propulsion system with improved propulsion performance by applying the quanta effect to VRT. The objective of the present study is to design the quanta vortex ring thruster, hereafter CVRT, to improve propulsion performance compared to the VRT. Contents of the present study as below. Computational fluid dynamics result which use the dynamic mesh techniques and mass flow boundary condition at piston plane are compared. Numerical analysis are carried out for validation with previous result of experiments and numerical simulations. Numerical analysis of VRT and CVRT are carried out. First, evaluation of propulsion performance with changing radius of curvature of the quanta wall was analyzed. Second, evaluation of the propulsion performance with changing the speed ratio of the primary jet and the quanta jet was investigated. Next, computational domain part. Computational geometry and domain for the VRT and CVRT as below. VRT and CVRT have the same piston diameter of 0.0245 meters. The piston diameter is exactly the same as previous experiments of Cardiff et al. Next, computational method part. SNOOFOAM is CFD solver based on OpenFOAM, which is developed by Seoul National University Think Tank Lab. SNOOFOAM consists of specialized in hydrodynamics problem of naval architecture and ocean engineering, such as cavitation, free surface effect, wave generation, and 6 DOF motions. Governing equations are consist of the continuity equation and incompressible NS equation. Temporal discretization is a second-order scheme, which is canonical scheme, and special discretization scheme is a second-order scheme. which is Gauss linear scheme. For pressure velocity coupling, the pinpool algorithm was used. The flow assumed two-dimensional axisymmetric problem, unsteady and laminar flow. Boundary condition of this problem as below. Next, result and discussion part. Comparison of CFD results due to the difference in piston motion implementation method. CFD results using dynamic mesh techniques and mesh flow boundary condition at the piston plane. Non-dimensional time scale, referred to as the formation time T star, is equivalent to the ratio of the piston length to diameter of piston. Piston stroke length is 6 times over piston diameter, and velocity program of the piston is constant velocity, which is 0.14524 meter per sec. Next, I compare the result of dynamic mesh technique and mesh flow rate method. The difference between mesh flow rate method and dynamic mesh technique up to 2.6%, indicating good agreement. Also, computational time of mesh flow rate method reduced by approximately 24% compared to dynamic mesh techniques. Implementation method of the piston motion was modeled by mesh flow rate method, considering CFD result and computation time. Comparison of voltage controls in ZG plane. As formation time increases, the vortex ring behavior are good agreement between two results. Numerical simulation results of Rosenfeld et al. And Zhang et al. And experimental results of Cardiff et al. Are compared with CFD results. First, I compared total circulation and vortex circulations. Cardiff et al. Defined formation number as the total circulation is equivalent with maximum vortex circulation, and it is a time when the pinch-off process is occurred. The formation number of the present work is good agreement with previous result of the experiment, and the numerical simulation considering the error is 1.57%. The pinch-off phenomenon refers to the separation of a vortex ring from a trailing jet. I also compared the velocity profile at piston exit, which was a good agreement with numerical simulation result of Rosenfeld et al. And I also compared voltage controls with numerical simulation results of Rosenfeld et al. Propulsion performance evaluation index, hereafter PPEI, is the ratio of the entrained energy by piston motion to the average kinetic energy in the direction of the piston motion over the entire domain EZ as an evaluation index of propulsion performance eta. And the velocity ratio of the primer jet and the coanda jet is set as lambda. I set the coanda jet exit length to 10% of the primer jet, and numerical simulation were conducted for lambda equal 0.5, 1, and 2. Propulsion performance of the CVRT is improved up to 15% in case of the lambda equal 1. CVRT is less propulsion performance than VRT at all curvature radius in the case of the lambda is equal to. As the speed of the coanda jet increases, the vortex ring and negative vorticity generated along with the trailing jet, and it is indicated that vortex ring formation is affected. If lambda is 2, the negative vorticity block the energy entrainment required for the formation of the vortex ring. This tendency is consistent with the result of vortex structure using quick criterion. If lambda is 0.5, the magnitude of vorticity of the trailing jet increases compared to the VRT. The vortex ring velocity of the CVRT is faster than the VRT due to the entrainment of momentum from quanta jet. If lambda equal to it was found that the pinch-off phenomenon of the leading vortex ring occurred due to excessive momentum entrainment caused by the quanta jet as the formation time increases. The negative vorticity generated by the quanta jet was shown to have a greater angle of inflow as the radius of curvature decreases, which is likely to block the entrainment of energy required for the formation of vortex ring. Finally, summary and conclusions. Comparison of the CFD result due to difference in piston motion implementation method. The piston motion was modeled by mass flow rate method, considering CFD result and computation time. Comparison of CFD result with previous results of experimental and numerical simulation for validation. CFD results are good agreement with results of previous studies. Comparison of propulsion performance of VRT and CVRT. Comparison and analysis of propulsion performance of the VRT and CVRT are carried out under 3 curvature radius condition and 3 velocity ratios. Quantitative comparison using PPEI and analysis in terms of the vortex ring formation and separation are conducted. If the radius of curvature is the smallest and lambda equal 1, the PPEI is the highest and show an improvement of propulsion performance approximately 15% propulsion efficiency over VLT. Thank you for listening. It's my
Okay,
presentation.
thank you. Thank you, Mr. Ho.
Yes.
Yeah. So, is there any question and comments from everyone? Or you can see the question from the website. Can you see any question online?
Yes, SNOPOM is the open source developed by OpenFOAM.
So SNU form, right? Is
Yes.
developed by the by your lab, right?
Yes. Yes.
Okay. So is it opened or not?
It is open.
You mean so everyone can get this code
Yes,
SNU
yes, SNU form.
Yeah.
I use dynamic mesh using by SNU form, and I open my code with yours.
I mean, is the anyone can get this code free or not?
I beg your pardon?
Yeah, I mean, is the possible to get your code of SNU form? Is it free or not? Yeah, means this code SNU form is open for use or not?
This is I developed code. Yes, so I shared my code with yours.
Okay.
Yes. Okay.
You can share your code.
Yes. If you want my code, send me email address and I share my code.
Okay. So, and another question is what's the real number for your this JEP jet propulsion. Yeah, how much the Reynolds number?
I beg your pardon.
I mean, how much the what's the number? How much the number? What's the Reynolds number of your calculation the case?
So about 6-7 cases, and including validation works. Yes, maybe.
How much? I mean, it's the Reynolds number. What's the Reynolds number? Reynolds number.
Reynolds number.
Yes.
Around 5,000 below.
1,000.
Yes.
Okay, because you said your simulation is
yes.
Yeah, the
Laminar
jet,
condition.
the jet
Yes.
propulsion, right? It's a high speed, right?
This case is not very high speed because constant velocity is 0.1524 meter per sec. So this case is laminar condition.
Okay.
Yes.
Okay. Anyway, thank you, Mr. Hall. Because now it's the time is up. Thank you, Mr. Hall. Yeah.
Thank you for listening.
Yeah. We move to the second presentation. Is the Lam, Mr. Lam, right? Yeah, Mr. Lam, please.
Hello, everyone. My name is William Lambert. I am a PhD candidate at Virginia Tech in the United States. And this is a short little project that I have completed with my advisor, Dr. Stefano Brizzolera, entitled Lagrangian-based nonlinear maneuvering and seakeeping parameter identification using OpenFOAM. To give you guys a quick overview of what I'll be covering today, I'll be first covering exactly what this Lagrangian maneuvering and seakeeping model is, and some of the parameters that actually need to be computed to populate this model. We did this using OpenFOAM, so I'll cover a little bit about how we exactly use OpenFOAM and how it is set up. And we did this using different impulsive motion simulations. So I'll go over some of the deeply submerged results, some of the validation cases that we used to identify this impulsive motion model, and how we're extending it to near surface conditions to incorporate some radiated wave conditions. So this Lagrangian nonlinear maneuvering and seakeeping model, shortened LNMS, was developed by Virginia Tech pretty recently, and it is an energy-based modeling primarily used for different underwater vehicles that are operating near this free surface where there are dynamic wave effects. And it's pretty much being used to be able to build feed-forward energy-based controllers for depth keeping and sea keeping parts for these underwater vehicles. So the final form is this top equation, and earlier on the parameters, these d phi dt terms, these derivatives were populated using boundary element methods if you look at those double integrals over the body surface and over the calm free surface. But we would like to further study these nonlinear effects using nonlinear codes. And so we take a few steps back and we look at the primary development of the Lagrangian term, which is the system kinetic minus the system potential energy. And we get a form that looks like this using different body parameters, such as different added mass terms, along with a convolution integral of these body kernel matrices. Focusing primarily on the impulsive motion part of this Lagrangian, this top line of the Lagrangian, we see 4 different added mass terms, which are shown here. So first we just have the the rigid body mass matrix, which is known prior. But then we have 3 additional added mass matrices. We have a deeply submerged added mass. We have a correction to the added mass that is the result of being near a rigid free surface. So the asymmetry in the fluid due to that, the presence of a rigid free surface. And then we have a further correction that accounts for the impulsive deformations of the free surface due to some acceleration of the body. So we're setting up a system of simulations to be able to capture each of these terms separately. So for our test, we used a 6:1 prolate spheroid, a pretty simple shape, and ran some deeply submerged steady state validation cases just to test the use of OpenFOAM and its ability to look at different inviscid and viscid fluids, especially when we move towards these impulsive accelerations from rest. When I say impulsive, I mean that we're running very short accelerations on the order of 1/100th of a second, so that memory effects, that memory convolution integral does not come into effect. And we're looking at this difference in the inviscid and viscid fluids to see if there could be a viscous fluid correction, especially when we go back to that original model that was based on boundary element methods. And we're looking at the motion in different degrees of freedom, so in surge or in sway. And we especially want to look at this near the free surface to capture that inclusion of the nonlinear free surface effects. So for OpenFOAM in particular, we're using the volume of fluid solver inner foam with the dynamic overset mesh to get that short impulsive motion. And when we have that acceleration, we decompose the force that is being experienced by the body in terms of an added mass portion and a velocity dependent damping portion that's linearly dependent on the velocity. So some of the simulation particulars for the viscous test, we just used incompressible Rantz equations with K omega SST turbulence modeling and a no slip condition on the body. For the inviscid, we also still use the incompressible Rantz equations, but with the laminar turbulence setting, bringing the dynamic viscosity very close to 0. We actually had to find an external boundary condition for the body. It's called my moving wall slip, to provide a slip condition on the body when the body is actually moving instead of having the fluid move over the body. So that's how we imposed the slip condition over the body for the inviscid case. Moving on to some of the mesh convergence studies that we looked at, the body was modeled using an overset mesh, like I said, and we added layers of refinement using snappy hex mesh around the body. So these are the 2 cases of the least dense case and the most dense case, adding successive refinement levels over the body. And just for reference and some pretty pictures here in this presentation, these are some pictures of the difference of a 0-degree pitch in the deeply submerged condition for both the inviscid and viscous case, just to give a sanity check on the simulation. And we see that the inviscid has very little wake. We see the 2 stagnation points at both the bow and the stern. Whereas in the viscous case, we see the separation occurring at the very trailing edge of the body. And we see that take place both in the vorticity that is also occurring over the body. So for this impulsive motion, we have cases of both pure surge, pure heave, and then a mixed case where the body accelerates in one direction with a steady pitch angle to that direction, shown here by this image. So for instance, this is a 20-degree pitch angle. And we see convergence to potential flow theory for decomposing this acceleration into the surge component and the heave component. So as 1 over the number of cells goes to 0, we see that the inviscid surge and heave respectively converge onto the potential flow theory. We also see slight differences when we pull out the added mass for the viscous cases. These still converge with the mesh, but do not necessarily converge directly onto the potential theory. This slight difference we attributed to the virtual increase in the body size due to the boundary layer creation next to the body. So now as we bring the body close to the free surface, we have these different free surface boundary conditions. As I mentioned at the beginning of this presentation, we have the fully rigid free surface, and analogous to that, we also can apply a symmetric boundary condition. In this fully rigid case, we have a wall with a slip condition imposed on that wall for the velocity. Opposed to both of these cases, we also have a fully deformable free surface with an atmosphere where the free surface is free to deform due to that impulse of motion. And also I call it an open boundary condition that allows the fluid to flow freely across this boundary, but there is no atmosphere, so there is no free surface deformation, but we still have that asymmetry in the fluid forcing. Looking at the actual added masses for this body operating in pure surge, as the diameter to depth ratio increases or comes to zero, we see a convergence onto the deeply submerged added mass values. We see that these open boundary conditions have values less than the deeply submerged values, and this is due to less fluid being accelerated when the body accelerates. But when we have the rigid cases and the symmetric case, we see increased added mass values that decrease as we get further away from that boundary. So some of the main conclusions, we see that this infinite frequency added mass can be accurately calculated through these different impulsive motions, neglecting memory effects. We also note that these viscous effects can be accounted for through this linear velocity damping term, with slight corrections being made because of the virtual increase of body size. We also note that the free surface effects can have a large impact on the added mass, especially for those small submergences, depending on if you're near a rigid wall or a freely deformable free surface. And as we move back towards isolating terms in this model, maybe varying these boundary conditions can further isolate those free surface effects. So to further these studies, we're looking at a different acceleration independence. So in these cases, we just ran a 10 meter per second squared acceleration, but seeing if these different acceleration has an effect, which it shouldn't. We're also looking at accelerations from steady states. So in a steady state simulation, we'll have some sort of wake being formed, especially in the viscous simulation. So if an acceleration from those steady states would have an effect. And we're also looking at other degrees of freedom, such as rotations. Thank you. And now we can move on to some of the questions.
Yes, thanks, Mr. Lambert, for your excellent presentation. Yes, yeah. Can you see any question from the website online?
Yes. So I did use an overset boundary set, but in those particular images, I pulled out the overset portion because it can get a little bit difficult when I'm showing the meshes, because it shows the background portion in addition to the overset portion in those images. So I just pulled out the overset boundary set.
Mm-hmm. So how do you consider taking into account the minority? You mentioned that you do the minority. So what kind of the mechanism to make the minority? So, for example, if you want to control your motion, so do you use some of the propeller rudder or something? But I didn't see any kind of this rudder or something.
No, it's a solid body motion. So I use a tabulated 6DOF to specifically set the motion I want the body to take.
Okay.
So right now it's just a bare spheroid that has motion imposed on it, almost like a virtual planar motion mechanism test.
Okay, I see. Okay. So this means at the moment you do some kind of the forced motion, right? Mm-hmm. It's the just the motion is the giving by your specified, right?
Yes.
Okay. So I see. Okay. So any other question? Okay. If no, thanks, Mr. Lambert, for your excellent presentation. Thank you. So let's move to the last presentation in this session. Will be given by the Mr. Feller. Mr. Feller, please.
Yes. Okay, I'm sharing my screen. So, okay. So, hello everyone. My name is Paulin Ferraud. I am CFD engineer. I am also the co-founder of GMAT Technology. So, GMAT is a private company specialized in numerical simulation in the field of CFD and finite element analysis. So today we are going to speak about naval application. So in an industrial constraint, we need accurate results, robust numeric, and short delivery time. So in this context, interfoam solver suffer from many limitations regarding hydrodynamic application. So the first limitation is the spurious air velocities phenomenon, which is widely reported in the literature. This phenomenon badly affects wave propagation exercises, and it's lead to an artificial increase of the current number. For steady-state application, interfoam generates free surface wiggles. So this is likely caused by Muller's algorithm for wave capture. And interface wiggles can be limited by increasing outer corrector, Muller's subcycling, or using smaller type step. But this is often unacceptable because it leads to a large increase of the calculation times. And problem becomes even worse with mesh refinement. And so, for example, for planning hull, convergence can be extremely difficult to achieve. So in this context, we decided to develop an incompressible wave free surface flow solver. And I will call GFM foam or marine foam in the presentation. So here is an example of the free surface wiggles phenomenon. So this is for the KCS hull, and this appears when you increase too much the time step. So this is with two outer corrector, 4 corrector, and 1 mule subcycle. So as you can see, this is not acceptable as a result. So for the marine foam governing equation, we start with a volume of fluid formulation, and we add the compression term as interfoam. We abandon Muller's algorithm to the profit of algebraic scheme. So we implemented modified 6A, modified Ashwick, and so on. And this is very important, is that we done that in a deferred correction approach to have a perfect stability. For the pressure velocity formulation, we use a one fluid formulation. So this equation is valid in each phase. And we had a jump condition at the interface. So note that we don't move the density inside the Laplacian term. So this is a difference with the reference paper of Vukiewicz. So the Gauss-Free method leads to a modification of Laplacian and gradient operator at the interface. So actually, the free surface become embedded in the discretization process, and fluid properties are then updated as follows. So as for interfoam for the viscosity, and for the density, we enforce a sharp transition at the interface. So here is an example of for the full-scale KCS. So you see for the VOF, this is very sharp, no smearing. And for the dynamic pressure field, we have a one cell transition due to the Gauss-Flynn method treatment. So now I move on to the test cases. So the first test cases is a fall of a water column. So from measurement of Gomez and Gesteira. So you have here the comparison in terms of force on the column and velocity in front of the obstacle. So for marine foam and interfoam, so both solvers quite good results, give quite good results, but we see that the peak force is a bit better predicted with marine foam. Okay, so now a test cases for wave propagation exercises in a periodic domain. So this test case is come from the paper of Larsen. So basically, you see you have a periodic domain and you initialize a wave. So the wavelength is equal to the length of the domain. So you have inlet and outlet periodic condition. So basically, the wave will travel infinitely in the domain. And we are using the AV schemes and AV solution of dambreak tutorial. So this is the methodology of Larsen. And we use mules in both cases, so for marine foam and interfoam, in order to be as fair as possible. So this test case will only show the advantage of using the Gauss-Flynn method. And what you can see here is that with marine foam, the wave height or the wave amplitude here is better predicted during the wave traveling. So here you have 100 periods, so 200 seconds of simulation time. So now I move on to steady state test cases. So this is a Chryso container ship. So this test case comes from the Gothenburg workshop. So this is test case 2.1 and 2.2a. So we use a fixed time step of 0.05 seconds. So this is quite large time step. It will lead to a core number of, if I am correct, something like 70. We will see this in a future slide. So we have 2 outer corrector and 4 corrector. And as we previously seen with interfoam, we must use 5 subcycles in order to avoid wiggles. So the calculation time with interfoam will be larger than with marine foam. So marine foam is only 1 subcycle and 3 VOF schemes. So here is the finest mesh with a snappy X mesh, so 3.6 million cells. And in this table, you have the comparison for force, so the ship resistance, or only the error in order to be short. So marine foam, Ashwick, modified Ashwick, and modified 6am. So as you can see, both solvers give good results to interfoam as well as marine foam. So the error is very, very low. So we are below 1% for the finest grids. This is very excellent, except for Ashwick, where the error is largest. We are going to see why. So here is a result on the midship cut plane. So we have on the right the result with interfoam and on the left with marine foam. On top, it's a velocity field. And on bottom is the dynamic pressure field. So as you can see, the Gauss-Flynn method leads to a one cell transition for the dynamic pressure field, whereas in not the case with interfoam, this is smoothed at the interface. And interfoam produce this light phase acceleration due to the imbalance of dynamic pressure gradient and density gradient. So this is not the case with marine foam. Here it's a comparison for the wave pattern. So as you can see, interfoam and modified Ashwick and modified 6am give very good results. So I recall here that we have 5 subcycles with interfoam, whereas it's only 1 with marine foam. And with Ashwick, you see that the wave pattern is badly calculated. All those features are not well captured by the schemes. This is why the force is not the error is the largest for the force. So for marine foam and modified 6am and modified Ashwick, the agreement is quite very good. So as we also can see on this graph, this is a wave cut line here. With Ashwick, the wave elevation is quickly dumped. So again, very dumped with in red Ashwick, All other results are very good, and also again very damped with Ashwick. On this table, I would like to speak about the minimal number of subcycles to avoid all wiggles with interfoam. So you have different time steps. So 0.1 is very large. It's a very large time step for this application. So we have the maximum courant number in green with marine foam, as well as the CPU time. And in orange, this is with interfoam and wheels. So if you have the minimum number of subcycles to avoid wiggles, and the maximum core number here and the CPU time. So we see, for example, for 0.05 seconds, that the calculation time is almost doubled with interfoam because of these subcycles. And the maximal core number is reduced by a factor of 2 with marine foam. So this increases overall solver robustness. Now the latest test cases. So this is a full-scale ship resistance simulation. So this is derived from the Lloyd Register workshop in 2016. So the ship name is Regal, and we have 4 velocity, so 8 knots to 14 knots. So you have example of the mesh built with NAPI, so 8.4 minute sail without symmetry plan. And because there is no experimental data, we are going to compare our result with the workshop submission results. And we are running simulation at Chrome max of 150. So this is a 0.2 second of time step. This is the largest time step of all contributions of the workshop. And as you can see, we have very excellent results and agreement with the overall average simulation of the workshop. For trim and sinkage calculations, this is also the case. So in red, this is a sinkage displacement. In green, this is a trim angle. And you have with the cross here, the average value from a workshop submission. And the blue line, this is the standard deviation. So only one standard deviation for this vertical line. So we have a very good agreement. And here it's an example of the result in terms of wave patterns for the 4 calculated velocity, ranging from 8 to 14 knots. So obviously, when we increase the velocity, the feature, the wave elevation increase. So for concluding, interfoam, overall good results. So, but there are intrinsically limitation regarding spurious air velocities that can destroy wave propagation, and this leads to an artificial increase of the courant number. And by the way, the user must use a very low time step due to this phenomenon. The free surface wiggle appear when you increase too much the time step. For example, if you want to decrease your calculation time. So in order to avoid that, multi-subcycling must be increased, but the bad effect that it will lead to a large increase of the CPU time. In another hand, with marine foam, we abandon mules to the profit of algebraic schemes. So there are no free surface wiggles, and the Gauss-Fluid method treatment allow us to capture a continuous velocity field across the free surfaces. And also, as a result of the Gauss-Fluid method, we obtain a sharp dynamic pressure and density field at the transition. So this is very interesting. And this drastically improves the wave propagation simulation. And finally, the present approach allows us to use larger time step while maintaining the accuracy. So thank you a lot for your attention. Thank you a lot also for the workshop organizer. And if you have any question, I will try to answer. Thank you very much.
Thank you, Mr. Fele. Mr. Fele, yeah.
Yes.
Yeah, can you see any question online?
Yes, there is a question of Mr. Guerrero. So in slide 7, there is lagging in the data. Any clue why? So slide 7. Why there is an offset? I think, so we analyze this, and we think that it's because in the experimental setup, the dambreak does not fall instantly. And this is the case in the numerical simulation. So obviously in the numerical simulation, we are going to hit quickly the obstacle, whereas it can be the case in the experimental data, because the I can say that the obstacle that is blocking the water column cannot be moved infinitely short, in an infinitely short time. So there is another question from William Lambert. So how is applicability of overset method in the solver? I don't know. I don't know how we can implement and use the overset library available in openfoam.com. I think it can be possible, but I don't know. We should check that. I invite you to send me an email and we can discuss more in detail about that. And another question of Joel. Any figure on computer testing time? I guess MarineFOAM is faster, but how many order of magnitude? It depends on the application. Here we are working on very favorable case because it's a displacement rule. So this is a KCS. So KCS is very favorable both for MarineFOAM and for Interfoam. But if you switch to planning rule, the difference can be very important in terms of calculation time between MarineFOAM and Interfoam. So I would say from our tests, because we have done a lot of tests and for the generic prismatic planning rule, we are 5 times faster with MarineFOAM than with Interfoam. So this is a very huge difference in terms of CPU time, especially when you have to run a lot of simulation for different velocity and for different mass. So a factor of 5. Mm-hmm. Okay, this was the last question. So thank you a lot.
Mm-hmm. Okay, thank you. So what's the GFM? Is it the ghost fluid method?
Yes, of course. This is ghost fluid method.
Okay, so this means you modified some of the pressure calculation scheme, right?
Yes, we modify the Laplacian and the gradient operator at near the free surface. So you need to determine when your free surface here. So it's well described in the paper of Vukovic, and based on that, you modified the extrapolation in both sides of the interface in order to modify how you compute the pressure. So this leads to a modification of Laplacian and gradient operator. So Gauss gradient and as well as least square gradients.
Mm-hmm. That's the GFM effective on the VOF or not?
Yes, it has a very good effect on the VOF because the volume of field method has a tendency to smear, and for example, you can have ventilation, and we observe that when you use the ghost field method, the ventilation is diminished. So we have less ventilation with the ghost field method than with the traditionally mixture formulation. So this is a very large improvement. So this has a lot of benefits for the solver. Okay,
it's good. Okay, so yeah, it's good. So any questions?
No.
Everyone, do you have any question? If no, let's thank Mr. Fellow again for your excellent presentation.
Thank you.
Yes, yes, thanks. So thanks all the speaker. Yeah, very good, very nice the presentation. Now we finished the 3 presentation. So let's all for all this session. Yeah, thank you
a lot.
Yes. So of the host, yeah. Yeah. So thank you for your join this session. So that's all. Bye bye.
Bye bye. Have a good day.
Yeah, have a good day.